So the first 6 problems for homework in section 9.5 are basically a regular series and then an alternating series. So you can see these two look the same, except you've got this -1 to the n-1 power. Likewise here, that these are two of the same. You got -1 to the n-2 power, and here you get the same. So the purpose of it is to look at the differences in the results as well as behavior. And you can, if you look on page 636, you'll see that the alternating series are B, C, and F, because they go up above and below the final curve, that where it levels out and comes to a stable value. So they all converge, all of these series converge. So what I'm going to do is just use spreadsheet to generate the results. So what we'll do is we'll share Excel with you, and we'll set it up for each one of these. So our first column will be N, and we'll go up to 10 terms. Okay, and then we'll do each one of the problems. So let me insert a row so I can put some identifying thing here. So there'll be problem 1, problem 2, problem 3, problem 4, problem 5, problem 6. Okay. And then we have A sub n and the sum. So we'll copy these two. Just paste, Control C, Control V, Control V, Control V, Control V, Control V. Okay, we've got all the columns set up. So now we need to write the equations for each one of these. So the first one, A sub n, is 6 divided by n. Oh, forgot my equal sign. I think I remember that one, too. 6 divided by, oops. Let me just delete that. Try it again here. Equals 6 divided by, there we go. And that's good. I've got to square it. Okay. The second equation is going to be equal to -1 raised to the n-1 power times 6 divided by n squared. -1. Should guess -1 to the n-1 times 6 divided by n squared. Okay. The third equation is going to be 3 over n factorial. 3 divided by fact. So that returns the factorial, okay, of n. Okay, that's good. The next one is going to be equal to 3 divided by, we've got to put our little alternating series part here. So I have -1 raised to the n-1 power times 3 divided by factorial of n. Okay. You see they all start out at 3, I think. If you look at all the problems, you'll see, except for C, which starts out at 5, so that must be what happens with the next two. They actually start out at 5. Okay, so the next problem is 10 divided by n divided by 2 to the n. 2 to the n. Okay, that's 5, yep. And then the last one is equal to the same thing, -1 raised to the n minus 1 times 10 divided by n divided by 2 to the n. I guess that should end up being 5 too. Okay, so that's the equation, and so we could copy those down if we wanted to. But let's just do the next part. So the sum term to start off with is just the initial value, and so we got that. And actually, we can just copy that. So I'm going to do Control C, Control V, Control V, Control V, Control V, Control V. Okay, so that is everything that the first row is correct. Now the second one, we can copy these down. So let's just pull it down one. That'll copy the saying this should be negative. So you can see the first two terms of 1 through 5 are both positive, and then the second term of the other ones are negative. So that's the whole alternating series nature of this thing. And finally, the sum for the second term, take the first term and add the new number. So there I get 7.5. So whereas here I'll get 4.5, and here I'll get 1.5, or 4.5, here I'll get 1.5. Here I'll get 6.25, and here I'll get 3.75. Okay, so those are all the second sum. This is S, capital S1, this is capital S2, this is A sub 1, this is A sub 2. So now we can actually just copy this whole row down until I get to row 11. And you can see here these these get really small quickly. So these are the numbers we should be looking at. So actually these are quite easy to recognize because the beginning numbers, actually we don't even have to do all this stuff. We could have figured it out otherwise. How is that? Well, it's because problems 3 and 5 start with 3. So if you look at the graphs, you see that, let's see, A and B start with 3. And A is the regular series, so 3 would match up with A. And 4 would match up with B. So let's just do this. So these both start with when n equals 1. So numbers 3 and 4 start with the number 3, and so you can look at A and B on page 636, and you see that they both end up with, they start with a 3, and B is the alternating one, so this is going to be A, this is going to be B. The ones that start with 5, the number 5, are going to be 5 and 6. So the ones that start with 5 are E and C. E and C. So we know these have to be either C. C is the alternating and C is the E is the non-alternating version. And then the other two start with 6, which would be D and F. D is the regular one, and F is the alternating. So I think we got everything A, B, C, D, E, F. Okay, so that would be one way of doing it. You can also look at the results. So let's just look at the numbers and see how they work out. So we see the one that starts with 6 and alternates, or doesn't alternate, is D, and you can see that levels off around 9 something. So that matches up with our result here. The one that starts with 6 that doesn't alternate, or does alternate, is F, and you can see it bounces back and forth and ends up being close to 5, which is this. The next one is the one that starts with 3 but does not alternate. That's A, picture A, and that levels off around 5, so that's correct. The one that starts, its first term is 3, but it alternates, is B, and that looks like it levels off around 2, which that looks right. Well, this one that starts with the 5, which is number, well, this one that starts with the number 5 is number 5, and the one that doesn't alternate back and forth is E, and that levels off around 7, so it's good. And then the other one that starts with 5 and levels and alternates is C, which levels off around 4. Okay, so those all look good. You can kind of see the values of the alternating parts. So you see these add all together, these bounce back and forth, but they both converge. This nth term is getting small enough, quickly enough, especially this one right here, that this does converge. Okay, so now we're continuing on. We're going to use the alternating series test, because the next couple problems are alternating series. Let's write down the problem. Okay, so that's the alternating series expression. So the actual a sub n is the part without the -1 part. So we get n over 2n minus 1. So the question is, for this thing to converge, is that a sub n plus 1 always has to be bigger than a sub n, and that this goes to 0 when n goes to infinity. So the first thing we should do is check to make sure that the limit of a sub n as n goes to infinity equals 0, question mark. Well, you can see that's not going to happen. The limit of 2 over 2n minus 1 as n goes to infinity is actually equal to 1. So this will not converge. Or it diverges. Okay, the next one is number 15. Yeah, I just looked at it. It's exactly the same as the previous one. I'm not doing a very good job picking these. So I'll have to pick a different one. Just to, okay, so the same thing's going to happen. If you take the limit of n squared over n squared plus 1 as n goes to infinity, that ends up being 1. Leading coefficients are 1. So again, for the same reason. So let's do another, let's pick 14 instead. And hopefully that one, yeah, that one looks like it works. Okay, at least it works for the first part. Okay, so that's it. So again, what we do is we first check to make sure the limit as n goes to infinity of a sub n equals 0. And so let's do it. Limit of 1 over the natural log of n plus 1 as n goes to infinity does equal 0 because you get 1 over infinity, which is 0. So that's check. First part's check. And the second part is that a sub n plus 1 is always less than a sub n. So 1 over the natural log of n plus 1, is that going to be less than 1 over the natural log of n? And so you can rewrite that as, is the natural log of n always going to be less than the natural log of n plus 1. What I did here is I just cross multiplied and kept this. So this goes over there and that goes over there. So the natural log of n always is less than the natural log of n plus 1. And we know it is because, you know, the natural log function is monotonic in this way. And so this is n and this is n plus 1. Then we know it's always increasing. So this is true. And so because both these true, then the series converges. Okay, let's go to the next one I assigned, which is 18. None looks exactly the same. It's weird. Every third one is the same kind of issue. Again, this doesn't go to 0. So that's an issue. So the limit of this thing goes to 1. So again, this diverges. Try to find one that's, well, let's just go to the next one again. So what we're saying here is if you take the limit as n squared over n squared plus 5 as n goes to infinity, what is that equal to? It's equal to 1 again. Ratio of leading coefficients in the highest order term is 1. Therefore, since the limit of a sub n as n goes to infinity is not equal to 0, therefore the series diverges. And well, I got a couple more in here. Maybe one of them will be different here. So we've got the sine of the summation from n equals 1 to infinity of the sine of 2n minus 1 over 2. Actually, the 2 is inside the argument times pi. So this may not look like an alternating series, but the issue, what you would find out is when n equals 1, you'll get the sine of 0. So this is n equals 1. When n equals 2, you get the sine of, you get 2 minus 1 over 2 times pi, which is pi over 2. And let's see, n equals 3 would be the sign. This is actually 2 times. Okay, so I got that wrong. When n equals 0, when n equals 1, you get 2 minus, so we get 2 minus 1 over 2 times pi, which is, this one's a sine of pi over 2, which is positive 1. What we have here is we would have 2 times 2, which is 4, so we get 3 pi over 2, sine of 3 pi over 2, which is equal to the sine of 3 pi over 2. So this is going to be 1, this one's going to be negative 1, and then the next one will be the sine of 5 pi over 4, which is 1. So it does alternate. But really all you got is, then you got the number 1, and then you say have 1, then you subtract 1, add 1, subtract 1, add 1, subtract 1. And so it never really converges, it just bounces back. So this also diverges. Okay, so that's those particular problems. Probably assign some different ones because these all seem to be cases where, kind of weird cases. Okay, we have one more simple alternating series question about convergence and divergence. This also involves a trig function. So we have 1 over n cosine of n pi. So what we're going to end up with is the cosine of pi for n equals 1. For n equals 2, we get the cosine of 2 pi. For n equals 3, we get the cosine of 3 pi. And the cosine of pi is negative 1. The cosine of 2 pi is 0. The cosine of negative 3 pi is negative 1. So actually it's just positive 1, not negative 1, not 0. So it does alternate, and so a sub n in this case is just 1 over n. So we have to answer the 2 questions. Is the limit of a sub n as n goes to infinity equal to 0? And the answer is yes, because if you put n equals infinity in there, you get 1 over infinity, which is 0. Okay, so that's the first requirement. The second requirement is that a sub n plus 1 is always less than a sub n. And that also is true. So if we put in n plus 1 and we put in n, we get that result. And kind of obvious that's going to be true because this number is always going to be greater than that number. So the reciprocal is going to be less. You can actually prove it by cross-multiplying it. You get that. And if you subtract n from both sides, you get is 0 always greater or less than 1? And the answer is yes. So this is true as well. So because these both are true, it is an alternating series. Then we can say that the series converges. Okay, the next couple of problems ask us a question relating to this remainder. So it says, use theorem 915 to determine the number of terms required to approximate the sum of a convergent series with an error of less than 0.001, and use the graphing utility to approximate the sum of the series with an error of less than 0.001. So it says graphing utility. What we're going to do is use Excel. So our series is summation for n equals 0 to infinity negative 1 to the n divided by 2 to the n over n factorial, and that is, they give you the actual answer. So this is an approximation to this. And later in the chapter we can see why that is the case, but we do have a number for the exact value now. So what we can do is we can list each term, and then we can look at this sum and then compare the difference between that and the exact value. So we're going to go to Excel now. Okay. So here we are. The first column is always n. So let's go 20 terms. Start off here. Okay, I don't think we'll need that many. Okay, this is a sub n. These are the terms. This is the sum, and this is the exact value. And then what we'll do is we'll look at the estimated error. Let me put another column, row in here. Estimated error and the actual error. We can compare those two. Okay, so our series, it's actually not just a sub n, it's the whole thing. So I need to put the whole expression. So I'm going to have -1 to the n power divided by 2 to the n divided by factorial of n. Okay, I got that right. 2 to the n over n factorial. Looks right. Okay, so that's the first term. And the second term, we just copy this down. And we start actually from 0, because I got a negative number there, so I knew something was fishy. So what we'll do is we will, let's delete that, and now we're going to fill it out starting at 0. Okay, let's just do 18 terms right now, see what happens. Okay, so those are the first two terms. And the sum, the first term, this first sum is just the first term. The second sum is we take the first term and we add the second term in column B. Okay, so that's the sum. And now we can just copy this down. And you see we're getting 0.60653. So it actually gets to the exact answer pretty quickly if that is the exact answer. So let's see, 1 divided by exponential of 1, e to the 1, is 0.36, square root. So 1 over the square root of e, 0.065, okay, there you go. So that's the exact answer. So we'll just copy that all the way down. And so the estimated error is what you do is take the term here, and so the estimated error for this one is this second term here. And let's see, do these an absolute value or anything like that? Yeah, so the absolute value of the remainder is less than a sub n plus 1. So actually, to get a sub n, we have to take the absolute value of this thing. So the absolute value of this number to make it positive. Okay, so that's the error. And the actual error is going to be this value, and we actually take the we're going to take the absolute value of this minus, actually it's not going to be this, it's going to be equal to the absolute value of this minus that. That's the exact actual error, 0.3347. So what it says is the difference between this and the actual, so this is the estimate error. Okay, so let's, so if you take the sum, the actual sum, the actual value, which is this, and you subtract this, it's going to be equal to the remainder, and the remainder is less than, this is less than the actual, the term. Okay, yeah. Okay, so what it's saying is that this value is always going to be less than this value. That the actual error is less than the remainder. So this will give you the, if you say the error is this much, you're going to be overestimating the error instead of underestimating the error, which is probably the thing you want to do. Okay, so now I think we can copy this down. So we get to the end. So notice this actual error is always less than this remainder. The remainder is the term, the one term beyond what we've used in the actual sum. And so what it asks here is determine the number of terms required to approximate the sum of the convergence series with an error less than 0.001. So this is my estimated error, 0.002. So this is the next one. This has an error less than 0.001. So that's 5 terms because we started at 0. And then it says use a graphing utility to approximate the sum of the series with an error of less than 0.001. So this would be the value with an error of less than 0.001. And it is. Here's the actual error, which is less than 0.001, 0.00024. So this would be our part B answer. And this would be our part A answer is 5 terms, since we started at 0. So the answers are okay, problem 41, just like we just did for 38. It's a different series. And so we have the series, the summation from n equals 1 to infinity of -1 to the n plus 1 over n is equal to the natural log of 2. Okay, so we're going to, again, we'll use a spreadsheet to do this calculation. A sub n is just 1 over n. So let's share Excel with you. Okay, so in this case, n starts with 1 instead of 0 like it did in the last case. We'll go down to, it's not taking that many terms because they're expecting us to do this by hand. And so what we have is a sub n, we have the sum, then we have the exact value, and then we have the estimated error and the actual error. And let me move those up so I can put error underneath them. Okay, so our function is equal to -1 to the n plus 1, right? N plus 1 times, or divided by n. I always want to put n, type n in, but that's not right. Okay, so that's a sub n. Okay, we do two of them here. So that's the next one. The sum, hold just a second, I accidentally pushed the button I wasn't supposed to. So the sum here is equal to the original value. The next one is the first value plus the second value. Okay. And then all I have to do is just start copying. Copy these two down 10 terms. See how quickly it converges. It's interesting. Make sure I did this right. It's not converging anywhere near as quickly. There will be a heck of a lot of terms. But maybe that's what they're trying to show us. -1 to the n plus 1 over n. Okay, that looks right. And our exact value is the natural log of 2. It's 0.693. Okay, so we copied that down. The estimated error here is equal to the absolute value of this thing. And the actual error is the sum, I've got to do the absolute value of the sum minus the exact value, which is 0.3. Okay, so the estimated error is this, the actual error is even less. And so we can copy that down like that. And something's not quite right. Oh, it's because I got to keep copying this thing down. So it looks like I need some more terms here, quite a few more terms. So let's go down to 100 just to make sure we get it this time. Probably don't need that many terms, but I'm going to, okay, there's 100 terms. And now we copy all this stuff down to 99. Actually, got 100. That's interesting. So, if you actually took these last two numbers and you average those together, you get very close to the right answer. So you see it's bouncing back and forth, and it's taken a heck of a lot of terms to do that. So I think this might be marginally convergent. Because to get an error less than 0.001 is going to take a lot of terms, And what I'm doing is I'm going to look at the actual equation that they derived that from. And I think that's it. Maybe I don't have it. Anyway, this is kind of marginally convergent in that it is coming to the convergent answer, but it's going to take a really long time to do that. You can kind of tell by, if you go down here to the bottom, you know, how much is it. You can see the error is getting less. The estimator is getting less, but it's in this third digit, and that's going to take a long time to do that? Well, we have a spreadsheet, so let's go a couple hundred here. Okay, 687 terms. Hopefully I didn't make a mistake somewhere in here. So just copy that down. 687 terms. So we're down to 0.001. We're almost there, but not quite. So it is getting there. It's just getting there very slowly. Okay, so the last group of problems are associated with this concept of absolute convergence and conditionally convergent. If you remember back to the first 6 problems we had for homework, those were all absolutely convergent because they were basically the same function. One was, you could say, was the absolute value. It meant it didn't have the -1 to the power term. So let me just demonstrate that for we. So number 1 was this. And number 2 was the same thing, except we had this -1 to the n-1 power times it. So if you take the absolute value of this, then you get that. So yeah, okay, yeah, that's true. Just want to confirm that by looking in the book. So both of these converged. So this one would be called, you would say it's absolutely convergent. Now, if this one didn't converge, but this one did converge, then it would be conditionally convergent. So let's write down problem number 48. So for this series, what we have, the original series, a sub n, the part that doesn't involve -1 raised to the power is this. And the 2 requirements for this alternating series to converge is that the limit of a sub n as n approaches infinity equals 0, which is true in this case, because if n is infinity, then you get 1 over infinity plus 1, which is 1 over infinity, which is 0. So that checks off. And also a sub n plus 1 is always less than a sub n. Again, because if you have a fraction, say you have 1/3, and then you add 1 to the denominator, you get 1/4. 1/4 is going to be less than 1/3. So that's also true. So it's convergent by the alternating series test. Alternating series test. Now if I just had the original function 1 over n plus 1, is that convergent? So the question is, how would you determine if that's convergent? Well, you could use one of these other tests, and this actually is a p-series. Well, what you do is you compare it with this one, so you'd actually have to use 2 tests, 1 over n. So that is, I think it's called the direct comparison test, and I'm going to look for that. So the direct comparison says if this is always greater than that, and this converges, then that converges. Okay. The problem there is that this one actually does not converge. Because that, if you go and look at a p-series, that's n to the p test. So if we go back to p-series, you have n to the p being 1, and it diverges if equals 1. So from that, we would say that diverges. So that really doesn't help us any. So then we have this ratio test. Actually, the limit comparison test. Let's try the limit comparison test. What it says is if the limit as n goes to infinity of the original function to the modified function equals some L, value L, then if this diverges, then that diverges. If this converges, that converges. So in this case, if we take the reciprocal of the denominator, we'll get 1 over n plus 1 times n over 1. And so we get n over n plus 1. And the limit, as that goes to infinity, is 1. So there is a limit. And since the series 1 over n diverges due to P series says that n to the p, if p is because p, the value in this particular case is between 0 and 1, it is actually equal to 1. And so because of P series, because of this requirement, diverges. So it's kind of a convoluted thing here. So this alternating series converges because of these two things. But the series that's not alternating, meaning it doesn't have the -1 thing here, just 1 over n plus 1, it diverges using the limit comparison test. Because if I take the original a sub n and I divide by a b sub n, which is similar to this, but something that actually I can evaluate, if this ratio is a limit, a number, which in this case it is, then if this diverges, then that diverges. Therefore, this is what we would call conditionally the original series, the alternating series, which I think was that, is conditionally convergent. So that was problem number 48. So let's actually prove what the heck they're talking about there. So I'm going to use Excel again, and we're going to look at both of these. So we're going to start with n equals 1, I think. Yep. Okay. So here's n. So 1, 2, and then we'll do 100 terms and see what happens here. Okay, 100 terms. So we're going to do two series. The first series is, well, we actually can just take the absolute value of this of the term. So the series is -1 raised to the n plus 1 power times or divided by n. And when I copy this, I should get positive and negative, positive and negative. I did it correctly. Okay, so you see it's positive, negative, positive, and negative. What I'm going to do here is I'm going to take the absolute value of a sub n. That will give me the other function if it doesn't have the negative, the alternating. So this one will not alternate. And so then I have my summation. I have my summation from my alternating series and my summation from my non-alternating. So here it's just equal to that value, and the same here. And then the next value in the sum is the first value plus the second value. And so we get 0.5, so it goes down. And if I copy that down to 100, you'll see the number is it's interesting. Which is, looks like it's approaching 0. It is approaching a number. It's approaching a very small number. Oh, it's over n plus 1. That's the problem, I think. So this, let's do this. It's not over n, it's over n plus 1. See if that makes a difference. Okay, so then I'm going to copy this down all the way. Still basically going to 0. Maybe that's the answer. Okay. Now what I do here is I copy this over to here, and you can see it goes up instead of down. And then if I didn't want to do that, undo that. Okay, so now I'm going to copy that formula down to 100. So you see it's growing, and it looks like, you know, it may level out. But according to our convergence test, it doesn't. So I'm actually just, that's not an odd number. So I'll have to wait till I get into the office to figure that one out, see if that is the correct answer, but I think it is, so we'll go with it. Okay, the next.
We're excited to welcome you to our first ever virtual D-School learning experience. We're about to give you a crash course in the methodology we teach here at the D-School called Design Thinking.
And when we started the D-School in a double-wide trailer in our first boot camp class, we asked the question, how could we create a 1-hour experience for the students that captured everything that they would experience in 10 weeks? And we created this 1-hour design challenge that you're about to go through. What I would invite you to do is to show up as a student again, to take your eye off the challenge that you're facing at home or at work or in your organization, and pay attention to the source of innovation that is you as an innovator, and see, by working on this challenge, if you could grow your capacity to work in a more human way, a more iterative way, a more collaborative way, and a more prototype-driven way.
In true D-School style, we're just about to get started. We want to warn you, it's going to feel fast-paced. It's going to feel like we're not giving you quite enough time to accomplish everything that we're asking you to accomplish. But what we're asking you is to trust us, to lean into the process, have a little bit of fun, and hopefully the experience that we all have together will allow us to have a really rich conversation and debrief, either as a pair with your partner or in your classroom or with your organization, about how the principles that we're going to highlight impacted the way you actually worked. The last thing you need to know before we get started is you need to make sure that you've got the right materials. You want to make sure that everybody in the room has one printout of the document that's called the gift.
It does not converge. We don't have to do any of the rest of the stuff. Okay, and then we have 54, which has this. Okay, so first, does the alternating series converge or not? Well, let's see. Does the limit as n goes to infinity of the non-alternating term equals 0? And the answer is yes. Because if you put infinity in here, you get e to the minus infinity, which is 0. E to the minus infinity is 0. Then the second question is a sub n plus 1 less than a sub n? And the answer is yes. If you were to put in n plus 1 here, and is that going to be less than e to the minus n squared? So what you'd have is you could break this way. You'd multiply the whole thing out, and you get e to the n squared minus 2n minus 1. And then you can break up and limit to individual terms. And these cancel out. So is this less than 1? Well, the answer is yes, because any e to a negative power is going to be less than 1. So both of these are going to be less than 1. So the product is going to be less than 1. So that's true. So the alternating series converges. Now what we do is we look at the non-alternating version of the series. And the question is, does that converge, and what test do we use to answer the question? So that's the big question right now, is which function could we use? So what do we have available to us? If you remember the last section, that gives a list of possible ones. So we have the nth term test, which would say that it doesn't diverge because it does go to 0. We already answered that. It's not a P series. We have the integral test, and that might be the one I think that's the one we want to use. So let's use the integral test, because the other ones involve trying to come up with the only issue is, that's okay, because at n equals 0, you still get a number here, so it's not like it doesn't exist. So what we do is we integrate from 0 to infinity of e to the minus x squared dx. Actually, we don't know how to do that because we need an x in the front. So that's not going to, we're still going to have to use the integral test, but it's going to be part of a larger thing. So what we'll do is we'll use this ratio or direct comparison test, I think it's called. It says if we take the limit as n goes to infinity of a sub n over b sub n, and that equals some L, limit L, then if this b function converges and this a function converges. Now, in this case, what I'm going to do is say the function's e to the minus n instead of e to the minus n squared. So that's because I can integrate this. So the integral test is going to be on this e to the minus n instead of e to the minus n squared. And both of those are greater than 0. Okay, so what we get here was we take the limit as b goes to infinity of the integral from 0 to b of e to the minus x dx. And that is the limit as b goes to infinity of, you get negative e to the minus x between 0 and b. And then you plug in the limits. So we get e to the minus b minus a minus e to the 0, and that is 1. And when you let the limit go to infinity, this goes to 0, so you just, so this is, first part is 0, the second part is 1, so the answer is 1. Okay. Yes. Now the question is this ratio? So this converges, so that's good. Now the question is, does this thing equal L? So let's try that. So limit as n goes to infinity of e to the minus n squared divided by e to the minus n, and that you get the limit as n goes to infinity of just e to the minus n. So if you take the reciprocal in this, you get e to the positive n. Then you add the exponents, you'll get e to the negative n. And the limit as n goes to infinity, this is 0. So L, 0 is a limit. It's not, it's just, so it can be 0 or any other number. No, it's just finite and positive. Yeah. So it's not positive, so that's a problem. So actually, I'm not sure what I need to do now. So I have my solution manual. This is an odd one or even one. It has to be an even one, doesn't it? Just to make life difficult. So I'm going to have to look at the solution to do this part.